Welcome to Deriving the Wave Equation Solution, Part A. So again, recall, we are working with the partial differential equation. Second partial with respect to t of u is equal to a squared times the second partial with respect to x of u. We also have the boundary conditions. U of 0t is equal to 0 is equal to u of lt. And then finally, we have u of x0 is f of x. And the first partial with respect to t of u evaluated at x0 is equal to g of x. So just like previously, we are going to, with the heat equation, we are going to run separation of variables. So we are going to assume that u of xt can be written as a function capital X of x times capital T of t. Then we have that the second partial with respect to t is simply x times t double prime. And the second partial with respect to x is capital X double prime times t. So if we go ahead and plug this into the second partial with respect to t is equal to a squared times the second partial with respect to x. We have capital X times t double prime is equal to a squared times capital X double prime t. And this becomes t double prime over a squared capital T is equal to capital X double prime over x. Again, for this to be true for all t greater than 0, so for this to be true, for t greater than 0 and x between 0 and L, these must be identically equal to a constant. So both sides must be identically equal to a constant. Which we will represent by negative lambda. So we have t double prime over a squared t is equal to negative lambda, and x double prime over x is equal to negative lambda. Or in other words, x double prime plus lambda x is equal to 0, and t double prime plus a squared lambda t is equal to 0. If we translate the boundary conditions, we have u of 0t is equal to 0, and this should be equal to x of 0 times t of t for t greater than 0. If this is true, the only way for us to have a non-trivial solution is for x of 0 to equal 0. So to have a non-trivial solution, we need x of 0 to be equal to 0. If we pick t of t to equal 0 for all t, then we would just have u of xt equaling x of x times 0, and we would just get the 0 function. Similarly, u of lt equaling 0 gives us x of L is equal to 0. So we wind up with u of xt, or we'll skip that. We wind up with capital X of x satisfies x double prime plus lambda x equals 0, with the boundary condition x of 0 equals x of L equals 0, and t of t satisfies t double prime plus a squared lambda t equals 0. Again, the initial condition does not translate into this separated variable situation, but our boundary conditions fortunately do. So this is what we will be working with. In the next video, we will go ahead and solve for these x of x and t of t.